In section 8.4, we're going to study definite integration. Definite integration is used in many applications of calculus, and today we're going to learn how to evaluate a definite integral and what a definite integral really means from a graphical sense. In future math classes, you'll have the opportunity to see where definite integrals apply as well. Say we're asked to evaluate the following integral. And what do you notice differently about this integral and the ones we've been doing so far? Well, I'm hoping you notice that these guys have numbers attached on the bottom and on the top of the integral sign, and those are called our upper and lower limits. Now, what this really means is if you were to graph the function 2x plus 3, okay, 2x plus 3 is a linear function. And when you want to find the integral from 1 to 4 of 2x plus 3, they're really asking you what is the area under the graph of the function 2x plus 3 from where x is 1 and x is 4 all the way down to the x-axis. So basically, the answer to this integral is really the area under the curve 2x plus 3 from 1 to 4. So if we calculated the area, that's the area of a trapezoid, and the area of a trapezoid, the formula is 1/2 the base, the short side, times the short side plus the long side. So on this particular trapezoid, the base is going from 1 to 4, so it would be 3. This would be considered my short length, which is 1, 2, 3, 4, 5. And this would be considered my long side, which would be 11. Well, if I add these together, 5 and 11 is 16. 16 times 1/2 is 8 times 3 is going to be 24. So the definite integral from 1 to 4 of 2x plus 3 dx is equal to 24. Now, the way we calculated it right now, we graphed the function 2x plus 3 and we calculated the area under the curve. There is, however, also an algebraic way to do this. So basically, if I apply my basic integration rules to 2x plus 3, so I add 1 to the exponent, so I get 2x squared over 2 plus the integral of 3 is 3x going from 1 to 4. I'm just going to simplify this first. And this would be, the 2's are going to cancel, so I'll be left with x squared plus 3x from 1 to 4. And now you plug in your upper limit first, which is 4. And then you subtract what you get when you plug in the lower limit. So 1 squared plus 3 times 1. If we work this out, I get 16 plus 12. Take away 4, and this ends up being 24, which was the same answer we got when we calculated the area under the curve. So basically what we just learned is a definite integral is really just the area under the curve of this function from this x value to that x value. So all we're going to do in the remainder of the lesson is evaluate definite integrals by using the algebraic technique. This is the general rule, which is also called the fundamental theorem of calculus, and basically it says if I have an integral, or I want to find the integral from a to b of small f of x dx, I take the integrand of f of x, which we're going to call capital F, and then we plug in the upper limit, and then we minus the integrand evaluated at the lower limit. So that's exactly what we did in the previous example. This is just the generic definition. So let's try this one. This is a very simple one. The integral of 2x is x squared, going from 3 to 5. So I plug the 5 in, plug the 3 in, 25 minus 9. This integral is going to be 16. This one here, I take the integral of each term. So this is going to be x to the 3 over 3 plus an x squared, going from 1 to 3. And again, you've plugged 3 into all of the x's in your integrand, so this is going to be 3 cubed over 3 plus 3 squared. And some people like to put square brackets to separate the upper and lower limit. So there's the upper limit. And now I'm plugging 1 into all of the x's in my integrand. So I get 1 cubed over 3 plus 1 squared. This works up to be 27 over 3 is 9 plus 9 minus 1/3 plus 1. So this is 18. Subtract. If I was to get a common denominator, that would be 4/3. And now to subtract 18, take away 4/3, I would need to get a common denominator. And 18 is really 54 over 3 minus 4 over 3. And if you subtracted, you would get 50 over 3 as your final answer. Now the next integral, we're going to do the exact same way. And I want to find the integral of cos. The integral of cos is sine x, going from pi over 3 to pi over 6. And you should realize that pi over 3 and pi over 6 are 30-60 degrees, so I need my 30-60 degree triangle. And if you remember, the sides are always in the ratio 1√3 and 2. So now this means the sine of pi over 6 minus the sine of pi over 3. Pi over 6 is 30 degrees, so the sine of 30 degrees is opposite over hypotenuse, so it would be 1 over 2. And the sine of pi by 6 is the sine of 60 degrees, so here's 60, it would be opposite over hypotenuse, which would be √3 over 2. And then we could just combine those over one denominator, and that would be your final answer. And that would be the exact form. Some textbook might convert that to a decimal, but we can leave it in the exact form. Okay, if we take a look at the next one, now we're asked to find the integral of sine x. Well, not the sine x, but sine 5x. So we could do this through u substitution, but we haven't really done u substitution with a definite integral. We're going to do that at the end of the lesson today. But we know how to integrate sine 5x based on our lesson of 8.2. So again, when I'm taking the integral of sine 5x, I take the integral of sine. And remember, we had sine, cos, negative sine, negative cosine. Going down is the derivative. Going up is the integral. So the integral of sine is negative cos, so it's going to be negative cos 5x, and then I divide by the derivative of 5x, which is 5. And this is going from pi by 10 to pi by 30. So I'm going to pull the negative 1/5 out, because it's a constant. And then this is cos 5x being evaluated by from pi by 10 to pi by 30. And right away you might be saying, well, pi by 10 and pi by 30 aren't exact angles. And you're right, but once we substitute them in, I'm going to get the cos 5 times pi over 10 is going to become pi over 2, minus, when I plug in a pi over 30, 5 pi over 30 is going to be pi over 6. Now you should recognize that these are exact values. So I'm just going to insert another page here. I get negative 1/5. The cosine of pi over 2, if you remember on your unit circle, pi over 2 is right here. And the coordinate of that point is 0, 1. So that's pi over 2. And cosine is the x-coordinate. So the cosine of pi over 2 is 0. Pi by 6, again, is 30 degrees. So we need our 30-60 triangle. And cosine is adjacent over hypotenuse, so that would be √3 over 2. And now negative 1/5 times negative √3 over 2 is going to end up being positive √3 over 10 is my final answer. Okay, if I want to evaluate e to the x, again, the integral of e to the x is itself being evaluated from ln 4 to ln 6. Now I plug in my upper limit, plug in my lower limit, and we talked about this briefly back when we did derivatives of exponential and logarithmic functions. But if you have e raised to the ln, because they're inverse operations, This whole thing just becomes whatever the function is inside my logarithm, so that is really just 6. Similarly, e to the ln of 4 just becomes 4, and this works out to be 2. And this is kind of a unique case, but there is one like this in your assignment, so that's why I did one in the example here. Okay, this one here, bells and whistles should be going off right now, because if I tried to move this up to the top and I got s to the minus 1 and I tried to integrate, if I added 1 I'd get 0, I'd be dividing by 0, and you can't do that. Hopefully you recognize that the integral of 1 over s is ln of absolute s, going from 5 to 10, which now would be ln 10 minus ln 5. And if you remember from pre-calc 30, if you're subtracting two logarithms that have the same base, you can combine them, provided you divide the 10 and the 5. So my final answer would be ln 2. Okay, now how do we use u substitution to evaluate definite integrals? Again, if you recall from u substitution in section 8.3, it makes sense in this question to let u equal x squared plus 1. du would be 2x dx. So if I divide both sides by 1/2, I get 1/2 du is x dx. So you notice I have an x dx here to get rid of. So now I'm going to do my substituting. And notice I'm not putting the limits on right now. So in place of the x dx, I get 1/2 du. And in place of the x squared plus 1, I'm going to get u to the 5th. Now, if you wanted to, you could integrate, resubstitute back in your x value, and use the limit 0 and 1, but that's a lot of work. What we can do is we can change the limits to fit for variable u, because the limits on the original question were for variable x. And all we're going to do is we're going to plug those in there. So if I put a 0 in for x, 0 squared plus 1, this new limit is going to be 1. If I put a 1 in there, 1 squared plus 1 is going to be 2. So now the limits 1, 2 are for variable u. So all I'm going to do is I'm going to integrate u to the 5th and get u to the 6 over 6 from 1 to 2. And now I'll just evaluate that. So I'll put a 2 in, then I'll put a 1 in. So this is going to equal 1/2. Oops, 2 to the 6th is 64 over 6, minus 1 over 6. So this ends up being 1/2 63 over 6. And if I multiply, I end up getting 63 over 12. And you can simplify 63 divided by 12, and you would get 21 over 4 is your final answer in reduced form. So that's the process to do a definite integral by u substitution. Make the u substitution, change your limits to match the new variable, and then basically go through your definite integral process again. All right, why don't you take a second and try this one? Okay, I hope you had a chance to try this question. And this one here, I would let u equal x squared plus 2x plus 5. So du would be 2x plus 2 dx. But notice I only have an x plus 1 dx. So if you divided everything by 2, you'd get 1/2 du is x plus 1 dx. So now, in place of the x plus 1 dx, I can put 1/2 du, and in place of the x squared plus 2x plus 5, you could put u. And now if I want to continue to work in u, I'm going to change my limits to match u. So I'm going to plug 1 in here for x, so 1 squared plus 2 times 1 plus 5 is going to give me 8 is my lower limit. And if I put a 3 in there, I'm going to get 3 squared plus 2 times 3 plus 5. It's going to be 9 plus 6 plus 5, and this is going to be 20. And now we are just going to take the integral of this, and I hope you realize that du over u is the same thing as 1 over u du. So my 1/2 is a constant. the integral of 1 over u is absolute ln u, going from 9 to 20. So this is going to be 1/2 ln 20 minus ln 9. And you could leave your answer like that. Or if you wanted to use your quotient rule for logarithms, you could rewrite it as 20 divided by 9, because we said that if we're subtracting logarithms and they have the same base, you can combine them, provided you divide the numbers within the logarithm. And there would be your final answer. So, definite integrals with u substitution, again, make the u substitution, change your limits, do the integration, and work it all out. So, there is your assignment for section 8.4. Again, if you have any questions, check the answers on the webpage, or feel free to email me.